for today, lecture number 5, a new topic and a separate module in the Canvas website, and that is this one. In gray there, all the stuff that we went through already, so all that we know. Stata, Canvas, nothing new. X's and Y's, we knew that beforehand too. The general logic behind all these tests, we've seen that before. 2 categorical variables, we know what to do there. 1 categorical variable, 2 categories with an interval variable, also fine. That's a t-test or a rank sum or a median test if the t-test is not possible here. And the continuation in interval by interval. I have 2 variables here. One that is interval and another one that is interval 2. And that ends up with being correlation and simple regression. And if I look at your own answers to the survey, because one of the questions in there was also, have you heard about this before? Many have. So this should be relatively easy to do, and the only thing is how to get the answers out of Stata. This is what we'll go through in Stata. These are the commands that you need, besides the standard stuff that we've done before. This one stands for correlation, and this is piecewise or partwise correlation, 2 slightly different commands. There's a command that's called Spearman that we're going to need. A command that is, I called it here reg, R-E-G. You can type regression in full if you want. Scatter and an lfit option that we need there. The predict command you'll see, and a command that's called egen. The E is for extended to, so we already have seen the generate command, generate, and then some new variable equal to, let's say, the square of the one that you have already. And there are quite a few, let's say, slightly more sophisticated procedures that you can use. For instance, standardize a variable, and for that we need something that's called an extension to generate. Okay, so we're going to go through a couple of examples with the data that we have. That is, here I'll show the results from last year, and you can do exactly the same thing with our own results from this year. But first, let me go through what these variables are that I'll take as an example. The first one is age by estimated income. Age, obviously, your age, and estimated income, that was that variable that we've seen before, where I asked you, what do you think that you will earn when you are 35? And the question could be, okay, is it the case that does the net income guess rise with age? So people who are older already perhaps tend to think that they earn more, or tend to think that they earn less. Could be either way as far as I'm concerned, and we'll see if that's actually the case. The other one is the current grade that you score compared to the high school grade that you had. So the question would be, does the high school grade predict the current grade? And to what extent does it predict that number? We'll go through that too. And, well, in fact, we're going to pretend that all these are interval scaled variables, and if you are really strict about this, you could argue for each and every one of them that they are not. For instance, even for age, you could argue that this is not completely interval. One reason would be, well, what works is the difference between 17 and 18, that's a year. That's exactly the same thing, and the difference between 33 and 34, fine. But on the other hand, it is bounded for sure below, and also quite sure above. So we know that we cannot end up, let's say, above 120 or so, and also for sure that we cannot end up below 0. So it's not completely interval, just like a, let's say, a normal distribution would be. Anything goes, even plus and minus infinity, and everything in between. But this one's actually bounded, but nevertheless we'll treat it as if it is truly interval. Same goes for estimated income. You cannot go to negative there, and also not completely to plus infinity, so that one's bounded too. Same goes for the grades, the current grade and the high school grade, but for all these variables we have that the differences between different values are well defined and well understood by everybody. So we'll take these as, let's say, interval enough. And there's another example that I'll show. For that I need 2 new variables from the data. This is one of the questions that you also had. Let's see if I can increase that a little. So there. These kinds of statements, you have a certain amount of intelligence and you can't really do much to change it. That will be the first one. Or your intelligence is something about you that you can't change very much. To be honest, you can't really change how intelligent you are. Okay, all these items are, let's say, rephrasing the same thing, that intelligence is something that you are sort of born with, and you can't do anything about it. And what you score, what you answer on these variables, that is a measurement of, well, what I labeled here fixed intelligence. That's the degree to which you feel that intelligence is something that you cannot do anything about anymore. And we had the same questions with all these items exactly in the same way, but then intelligence was substituted by talent. So for talent, you have the same kind of questions, and you have a score there too. And again, this gives us two interval scaled variables. Oh, and before I go there, this once again is how we calculate these through the alpha command. You'll see here, I pointed at that one previous time when we used the alpha command before as well. Pluses and minuses, and these pluses and minuses exactly coincide with here the questions that are phrased positively and phrased negatively. More on that in the chapter on scale scores. For now, look at this as, okay, we're sort of averaging out these items, but what we do before averaging out is reverse coding all the ones that are phrased in another direction. So think of this as a mean score on these separate items. Same for fixed talent, and I also made sure that the variable itself is coded in such a way that the name itself suggests that higher is more of that. So if the variable is called fixed intelligence, if you score higher on that, then you believe stronger that intelligence is fixed. And in general, I think it's a good idea to code your variables in that way, so that you do not have to think what exactly is that thing measuring and in which direction is it measuring. Which is also why I think, for instance, that in a data set, it's never a good idea to code a variable gender for male and female, because it makes you think all the time, okay, was the one the male and the two the female, or the other way around? So it's usually smarter to code it as either male, then male equal to 1 and female equal to 0, or the other way around, code it as female, female equal to 1, male equal to 0, so that you can see from the name of the variable exactly what it is. Okay, so that gives us three sets of two: age by estimated income, current grade by the high school grade, and whether you believe that intelligence is fixed as related to whether you believe that talent is fixed. The first thing to do when you have data of this kind and you want to know what's going on is just look at the scatter plot and get a feel for what's going on there. The stated command would be scatter yx. Here you see precisely these three, and well, this doesn't look like much. Here, sort of, you see that there is a relation between the two, and this looks a bit strong in terms of the relation between the two. And if you want, you can try to find a best linear fit through a command that is called lfit. So we have the scatter already. These are two vertical stripes, and then you just type behind it lfit yx. That will give you the line, not as thick an orange one as I have here, but I made it thicker so that you can see it better. And here you see that, well, let's say loosely speaking, on average it is the case that the older you are, the lower the estimated income that you think you're going to earn. Here, your average grade on your exam list, higher grades indeed go with higher grades at the university, apparently. And the other one, I don't remember exactly which is on which axis, but for sure you see here also a positive relation, which is what you would expect. If you believe that intelligence is fixed, it's likely that you also believe that talent is fixed. Okay, so that is already one idea here. You see this one's not so working so well, this one's slightly better, and this one's still better, but still not great. And just to show you what one looks like where the correlation is stronger from the soccer data that you've seen before in one of the other modules, there we have for a bunch of soccer players their height and their weight, and obviously you would expect that there is a relation between the two, and indeed if you put weight here and height there, you see that there is a strong relation in the sense that, well, if I would know height, I would have a pretty decent idea about what the weight would be, as you would expect. Okay, so all these kind of things, trying to estimate the best fitting line in there, and the way in which we do it, that is vector algebra. So just to make that as clear as possible, what we're trying to estimate the orange lines is this thing. This is for the first one. We have a vector here that's estimated income for the first person in the data, and the second and the third, and number 190 in this example, equal to, well, a scalar b0 plus b1 times person, age of the second person, and so on. And what we let's data do is try to figure out what these numbers are. So here, what the B0 is and what the B1 is for this line over there. But all based on vector algebra. Okay, now let's see. Correlation is defined as the extent to which a straight line fits the scatter plot. If it fits well, great. If it doesn't fit very well and you get noise, well, too bad. It's very often called rho, the Greek rho, and that is the correlation in the population. We use Greek letters for that. Or R, when we calculate the same thing, but then on the sample. So in that sense, it's nothing different from what we've seen before with these Greek letters. And the name for it is the Pearson product moment correlation coefficient. So every once in a while you might see that in a book. You might wonder, oh, is it something totally different from what I'm used to and what we normally call correlation between two variables? It isn't. It's just the same thing. And it varies between -1 and +1. And now let's go through what the different values represent. Here you see a couple of examples of different rho values. For instance, there, it says -1 over there. It's negative because the slope is pointing downward. And it is -1 because all the dots here are exactly on the line. So we have a perfect fit and a negative. There, the opposite case, rho equal to +1, is positive because we have an upward sloping line. And it's 1 because all the elements, all the dots are exactly on the line. And as soon as we get dots that are not exactly on the line, which is typically what we always have, we have different values. This is something over there. Okay, it's sloping downwards, so it's negative. And it has dots that are not on the line, so the fit is not perfect. So it must be somewhere between -1 and 0. Same thing for positive ones over there. Upward sloping. So the extent to which it is upward sloping here doesn't matter at all. But whether or not these these dots are on the line, that does matter for how large this number is, and we'll see that in a minute. And here, noise, there is no relation between the two, or stated differently, if I want to know what is on the vertical axis, it doesn't help me if I know what is on the horizontal axis. That would be a correlation coefficient of 0. Okay, so a couple more examples just to give you a feel for the numbers. There, 1 or close to 1, totally on the line. -1, same thing, on the line with downward sloping. And here you see, let's say, loosely depicted what different values would be. So this is 0.4, this is nothing. And you have to get used to that difference because, from a distance, this one is not so different perhaps from that one. But it does make quite a difference in terms of correlation. Then, just to make that clear once more, here we see that all these lines fit equally well, and they have a different slope, but that doesn't matter. Slope is not an issue. They fit perfectly, and upward sloping, so 1. And here we have -1, they fit perfectly, and they are downward sloping. This one is a bit of a weird one, where correlation itself is not so useful after all, because this is that we have a horizontal line here, so apparently x is varying, but y is at the same height all the time. So there, relation between the two, one of the two is a constant actually in this example, so there is not likely to be a relation between the two at all. Finally, an important thing to realize is what we're trying to fit here is a straight line, and the only thing that we look at in terms of correlation here is whether or not a straight line fits. And here, for all of these, you see that there are systematic issues in the scatter plot, obviously, for all of them. But in fact, all of these would show you a correlation of 0. Because in this case, these best fitting lines go straight through there, and there, or all horizontal lines. So finding that the correlation is 0 need not mean that there is no relation. It's just meaning that there is no linear relation between the two, nothing else. It's good to get a feel for what these numbers are. And one way to do it, let's see if I can get that to work, is to go to a website that's called Guess the Correlation. I think I have that here somewhere. So this is looking like old school Pac-Man kind of games, 8-bit games. Guess here what the correlation between the two is, and the aim is to stay within, I think, 0.1 of the true correlation. Okay, so give me a guess. What would the correlation be? 0.4? Very good. Was 0.45, slightly higher, within 0.1. You're doing well. The number one of a perhaps larger streak. Let's see. Correlation is, let's go again. 0.8. 0.86. Wow, you're good at this. That's good. 0.3? 4? 3 or 4? 3. Okay. Ouch. 0.51. You lost one life. Okay, somebody else. Give me a number here. How good is this? 0.7. 0.7. I think that's on the low side. 0.84. We lost another life. Our last life. What's this? Correlation of? 0.1. I hear a 0.1 over here. I'll go with that. 0.23. Kind of surprising actually, because this doesn't look like much, but still a correlation of 0.23. You know, to try to find a couple of these correlations in the actual data may very well be that there are not so many. And so even for very low correlations, where you do get a number, the cloud looks like that, which is from a distance not very good. But still, it works in terms of relation between the two. Okay, so try to practice that for yourself a little bit to get a feel for how that works. And the extent to which the line is fitting the cloud of dots, if you go online and try to find an actual formula for this, there are quite a few around. And here you see a couple. These, well, yeah, may look complicated. In fact, it's not that complicated actually. It has to do with the extent to which x varies from its mean and y varies from its mean, divided by how large the differences in general are. Well, not so weird. There are different ways to calculate the same thing, for instance, like that. And it's not too easy to get an actual intuition for this. And the intuition is actually way easier if you look at it from a different angle. And the angle would be, well, what would it mean if we try to fit the best fitting line here? And that is where we look at these kind of graphs. Two random variables, x and y, don't even know what they represent here. But what we're aiming for is a line that fits best. So we have to define the extent to which this line is missing the mark, so to speak. And the standard way to do it is you simply look at these distances. How far is that thing from the line? How far is that one from the line? And so on. You do that for all dots that you have. You square these numbers and you add them all up. And the best fitting line is the line that has the lowest sum of squared differences. And obviously you could do this in different ways. You could, for instance, just take an absolute value to get rid of the minuses. That would also give you a best fitting line, but according to a different criterion. But we typically don't do it. You could do something different here, raised to the power of 4. That also works. But the standard is, and there are good statistical reasons for it, that we won't bother with now, to use a squared. So this is a least squares line. This is also why the whole thing is called ordinary least squares. And the other thing that I wanted to focus on here is that although I'm starting to talk about correlation, in principle, what we're doing here is the same thing, simple regression. We're trying to predict y from a single x. And that one is called ordinary least squares. And they are related. And we'll go through the motions to show you exactly how the two are related in this case. Okay, so first, as you might get, this is basically a linear algebra problem. We're trying to minimize something here, the sum of the square differences. This is my y variable. This is the estimate of the y variable that I have. I'm trying to find the one that fits best. So we're trying to find b0 and b1 here in such a way that this sum of square differences is minimized. You can do the motions here and come up with an actual closed form solution that looks like this. The formula like that for the best fitting b1, and best fitting for that normally we use the hat. And b0 is then the mean of y minus the best fitting b1 times the mean of x. So this is a closed form solution. This is also why I stayed out really fast in calculating this. There's no iterative process converging to something. It's just there's a formula for it, and it's being filled out, and that's it. What Stata will do is give you the best fitting line if you ask it to run a regression, REG for regression, or type in full regression YX, that'll also work, and then you'll get the answer. So here is one example, height on weight. This is getting the soccer data. This gives you a lot of stuff back, and we go through what all of these things mean in a minute. But for here, the most important part that I wanted to show is this part. You see here that we get two coefficients back, 0.73, say, and 126. And these are the B0, that's the constant over there, and the B1 that fit best. If you want to fit, let's see, height from weight, that's also something that you need to remember. You put the y variable in the front, and that matters because later on we'll try to predict y variables from more than just a single predictor variable. So you need to start with the y variable and then all your predictor variables. In this case, that's only one. So what we have here is, well, that line that we fit through the cloud of dots looks like this: height equal to 125.78 plus 0.73 times weight. And the easy interpretation of this is, well, I know that assuming that weight is measured in kilos, if you have an extra kilo, in all likelihood that gives you 0.73 centimeters extra on average in the data that we have. Any questions about this? Finding the best line. Stata does it for you, and the numbers are there. Okay. Age, let's see how that works. Regress estimated income on age, and what we saw before was that the slope of that line was downward, so we get a negative number in over there, minus 38, and a constant there is, let's say, about 5,000. Same numbers, same spot for the numbers once again. And the line we also get about 5,000 minus 38 times age. So if you're a year older, then on average you estimate 38 euros per month less, apparently. That's what we find in our data. Okay, now I'm trying to figure out what's over there. And we'll go through what these numbers there mean. By looking, yeah.
I have one question. So the minus 38 is not the slope. Because before it was 0.73, so I thought that was the slope of the line.
That is the slope of the line, yes.
But you said that the value is between -1 and 1.
Oh, yeah. Good point. So we started out with correlation, and that correlation is between -1 and +1.
Okay.
The borders included, actually. Okay, put that aside for a minute. Now we're starting here with regression. We're trying to fit the best fitting straight line, and somewhere hidden in here is that actual correlation, and we're getting there where it is. That's basically what we're doing. But you're right, this is the slope of the line.
Okay, but this is regression.
Yes.
But if you turn this around, what's the starting age of the earnings are? Can you see that from this data?
What do you mean by the starting age?
Yeah, because if you assume this, a baby of 0 years old would earn almost 5,000. If you were 1, you would earn less, right?
Yeah, not necessarily earn, but would have an estimated income. So all these are based on the data that we have. And in our case, the data are, yeah, I know, age between, let's say, yeah, what have we, but certainly not close to 0. So let's say 18 plus, and then all the way up to 30 perhaps, for a couple of cases. So this is simply estimating the best fitting line on the data that we have. And because age here is at most, let's say, 30, then the lowest estimate here would be 30 times 38, and that we subtract from this number, which would still be fairly okay. But you're right, I mean, for all these you have to worry about, okay, so for which kind of population here do we feel that this is a reasonable estimate? Yes.
So that 38 number is the covariance of the variance?
No, I not even mentioned covariance or variance.
That was slide before, right?
Which one?
No, there was a formula there.
Oh, yeah, okay. You mean that?
Yeah.
Yeah, this is the covariance of x and y over the variance, but I'm not sure if this helps you intuitively. If it does, good for you. but this b1 half is that number over there.
Yeah, and the 38 in the other one.
And the 38 in the other. Exactly. Other question?
Yeah.
Yeah.
Yeah, just for my convenience, like the estimated income is on the y-axis and age on the x, and if you do it reversed, it will be reversed.
Yeah, so depending on which of the two you type first over there, this one here, estimated income, you get over there, age, you get over there. And this second one, is the x is the horizontal axis. Yep. And you can do it the other way around as well. Anything else? Okay. Now let's see. To get a feeling for how well we are predicting here, one thing you could do is, well, let's think about what, let's say, the stupidest but still sort of reasonable prediction would be. If we would predict simply the mean of y for all cases, that is not making use of any kind of other variable to predict y, so I'm not even using that x variable at all. So for instance, what we have here, estimated income, I do not know what the mean of estimated income in the data is, but let's say there's 3,500. Then here what I could do is, okay, I simply estimate 3,500 for all the cases in the data. In all likelihood, that's not very good, and we could try to sum up how bad it is. That's called the total sum of squares. So we look at 3,500 and we compare it with the actual value. That difference we square, and we do that for all the cases in the data. And all these differences squared we add up, and that gives us one number. That's called the total sum of squares. The extent to which you are missing the mark, so to speak, by just using the mean of y as a predictor. And to see how well you are doing with your predictor variable x, as we see here, you can look at the line. Yeah.
How is it different from regression? Because in regression you also use the sum of the squares and then try to find the best line, right?
Yeah, well, the difference is exactly in here I'm doing nothing. I'm predicting simply by the mean. This is my y variable, let's say, and okay, the middle is somewhere over there. I'm going to get the middle for all cases, which is obviously not very good. It gives us a, let's say, a control with which to compare.
Because the sum of squares is the smallest, then you get the best fit, right?
Yeah. So you'll get a huge number here if you just predict by using the mean for y.
So it's just an indicator, it doesn't do anything for you.
Well, if I would have a perfect model, if somehow I could predict y from another variable x, and I would have all the cases exactly on the spot, and I would then calculate the sum of the square differences, I would get at 0. Okay, so the best model I can have has a sum of square differences of 0, and let's say sort of the worst that I can have has a sum of square that's, this number. I start with the mean, I look at how far away am I square it, and I do that for all the cases. And we're now trying to figure out how much better we get when we use x as a predictor variable. When we use x as a predictor variable, we're trying to do this, we're trying to find the best fitting line. As soon as we have this, these predictions get a little bit better. I now get closer to my actual y, at least if I have a decent predictor variable. Now I do the same thing. I look at my predictions, and I look how far away am I. That's called the model's sum of squares. And comparing this to that gives me an idea of how well or how poorly I'm doing. Okay, so perfect model is I'm right on the spot, sum of square differences is 0. And a very bad model is somewhere over here. I have a huge number of sum of square differences. I want to be over there near that 0. I'm now using x, and the question is how close to that 0 am I getting? And that's one way to determine how well we are predicting here. In fact, what's that? This is how we define model fit. You see here model sum of squares and residual sum of squares. And these two are exactly the ones that I talked about a slide ago. And the extent to which you actually reach 0, or I should say how far you already are on your way to 0, that is a measure of the fit of the model. That thing is called R squared, and it's defined like this. The sum of squares for the model over the sum of squares in total. I subtract that from 1, and that is a measure for model fit. Yeah.
Is that also a measure for if the model doesn't fit well, then we should look at no straight line, but for instance, a different shape?
No, we're not looking at any kind of, at this point, no different shapes than just lines. So the only thing we're trying to do here is come up with a line that fits well, and we're trying to figure out how well a line is actually fitting. No parabolas, square roots, or what have you. So if our predictor variable x here, weight, wouldn't help us at all in trying to predict height, that would mean we get an r squared that is 0. This is perfect. Sum of square differences is 0. This is where we start by just guessing the mean. And having x to predict doesn't bring us much closer to that 0 number that we want to have there. So we look at how far have we gone in that direction, and well, if x is not helping, then 0. R squared would be 0. If we're totally there, we're now predicting perfectly, R squared would be 1. All based on these sums of square differences, and you see them over there. And these numbers over there are used to calculate this number over here. R squared, 0.57 in this case. So here we use these sum of square differences to come up with a measure of fit, and now we get to the relation between correlation and the simple regression, because R squared, well, think of this, the R in R squared as the correlation between your predicted Y, based on X, and your actual Y. And here, if you would take the square root of this number, then you would get the exact correlation between the two. But there was a question somewhere over there. Yeah.
So the model is the square of the differences between the mean, and the residual is the square of the differences from the model line.
Yes. Okay? The two ways to do the same thing, basically, and to show you that it actually is the same thing, I have the example right here. So again, regression of height on weight. This is the same table that we saw before. And I can also type here the correlation between height and weight. And here is still to be 0.75. There's another way to do the same thing through piecewise correlation, partwise. I'll get to what the difference between the two is in a minute. And here you see that, well, correlation is 0.75. If I would square 0.75, and I do that right here, I exactly get the 0.57 that I already had over there. Okay, so here you see, if I have only one interval x and one interval y, I can calculate the correlation through that correlation command, and I could have gotten that as well from something that's called simple regression by looking at that number over there. Okay, any questions about this? Yeah?
What's the difference between core and VW core?
Give me a couple slides and I'll go into the details of that. Anything else? Okay. So let's see, just to give you a feel for what this meant, because we looked at before. And I talked about that it is useful, the whole data stuff, to try to predict something from something else. We had salary predicts performance, and that actually worked out quite well. In fact, an R squared, at that point you didn't know what that was, now you do, of 0.92. So the correlation between salary of a whole team and performance, I think, over a season is actually really, really high. The square root of 0.92, which is close to 1, actually. So salary does predict how well teams are doing, quite well. Whereas the transfer sums don't predict it very well. There is still a relation between the two. 0.16 is the R squared, so the correlation between the two is the square root of that, but it is way, way less, just to give you a feel of the kind of results you can find. Okay, then one other way that you need to have seen in which these two are related, and for that we need standardization. And we've seen standardization a couple times before. I'll just show it to make sure that you have now definitively seen this and also know how to do it in data. If you have a variable, any variable in your data, standardizing the variable would mean creating a new variable that's equal to, well, the original one that you had, minus its mean, divided by its standard deviation. And the way to do it in Stata is quite straightforward.Egen for extension to generate, and then you give the new variable a new name. I usually do something where I type the original one, x underscore, and then standardized equal to, well, the standardized version of x. So that's the way to do it. And if you happen to forget that command, you can do it by hand. If you look at a summary statistic of x, you get the mean and the standard deviation. So if you would find there that the mean is 5.2 and the standard deviation is 1.3, then you can do it by hand to generate that variable equal to this. Not as precise because you're missing a couple of decimals here, but nevertheless, it's also quite close to a standardized variable. And what happens if you do this? Well, let's see. If you have standardized all your interval variables, well, what will happen is, for all these, they had a mean, that variable, and they now have a mean of 0. This is straightforward from the fact that you subtract the mean from it. And they have a standard deviation now of 1, given that you divide it through s. And that will mean that all the interval variables that you have are now on the same scale. And that might be useful as soon as you are trying to figure out which of a set of predictor variables is most useful to predict some interval variable. If you would find, let's say, that the coefficient, so the slope of that regression line is 0.01, which may sound like not a lot, then it makes a difference if the variable that is behind it, so the actual x, varies between 0 and 10 million, because 10 million times 0.01 is still a big number, or varies between, let's say, 0 and 10. And then you have to know for each and every variable, when you look at it, what the actual scale is of the whole variable. And if you do this, all variables are sort of scaled back to the same level. In fact, if all would be normally distributed, then what you would have is that they are 0 on average, and let's say loosely ranging between -3 and +3, all on the same scale. And that might be useful for, will be useful for multiple regression later. Okay, so that is standardization, and what we can do is, instead of the original regression that we have here, again, regression of height or weight, standardize these two variables, like this, related to standardized height, through that egen command, and then you see happening indeed what I already suggested. You get new variables here with a mean of 0. This is 3 times 10 raised to the power of -9, which is for all practical purposes 0. Same thing for that second one, and a standard deviation over there of 1. So now both are actually on the same scale. And now I can rerun the same regression. Let's see what happens there. There we have the original one on top, and now the regression with standardized height and standardized weight, and lo and behold, we have now the coefficient there that is 0.754, and that was exactly the correlation that we saw before, and that's no coincidence. So there's another way to interpret what correlation between two variables means. It means if you run a regression of the standardized variables on each other, that coefficient over there, the slope, is exactly the correlation. Do note, by the way, that all the stuff over here hasn't changed, so how well the thing is fitting r squared, still exactly the same number, which is sort of intuitively clear. It would be weird that if you change the shape of the variable a little bit, you get a totally different measure of fit. But this is indeed, that one I forgot, another way to try to find the relation between the two by looking at that number over there or that number over there. Okay, well, let's see. Yeah, that one I needed to add, just to make sure that you have it in the slides as well. Correlation coefficient, the regression coefficient of x on y after you've standardized x and y separately. Yeah.
So the regression of standardized variables is correlation.
That's really loosely formulated. The effect of x on y, so the slope of x there, which one? 0.754. That is exactly equal to the correlation between x and y. If you do this standardized, right? So you have x and y. If you run a regression, then you can find correlation in the r squared, because it's r, square root of r squared. Or what you can try to do is standardize both variables and then look at the coefficient of the standardized x on the standardized y. All the same thing. Ones that we had in our data, we now know that correlation and simple regression are sort of two ways to do the same thing. So here you have it. Correlation between estimated income and age is, well, close to nothing, minus 0.05. And you can see that back here, of course, in the r squared. You do not see that direction back anymore. The r squared is 0 or higher than 0 always. But you would find that if you take the square root from 0.0024, that you would get 0.0487. So here you see this happening. Same thing for the second set, current grade and high school grade. There we see a correlation of about 0.4, which is certainly quite a bit higher, and an r squared, therefore, of 0.14. So that one is a useful predictor of the other. And for fixed intelligence with fixed talent, we see a similar correlation, 0.38 or so, and of course then also a similar r squared of 0.14. Okay, now the correlation commands versus partwise correlations. Both of these commands will allow you to give a longer list of variables so that you get back all the correlations between these separate variables in one table all at the same time. If you have a data set without missing values, so there is not a single missing value in your data, then both of these commands deliver you exactly the same results. However, they differ exactly in the extent to which they treat missing data. What you get here for the correlation command, so not the partwise in front of it, is what Stata does first, is for all the variables that you have, determine for which cases in your data you have all these variables. And it might be that if you have a couple missings here, and a couple missings there, and a couple missings here, and there, that the number of cases that you end up with is seriously smaller than the set that you started with. In any case, what it will do here is calculate these correlations on all the cases where you have all these variables, and that will be of use later on when we encounter multiple regression. If you're simply interested in, give me the correlation between the two variables in the data for all the cases for which you can calculate them, then you do this partwise correlation. Now what happens is this coefficient over there, which is the correlation between age and income estimate, is equal to minus 0.0057, and this is calculated on all the cases for which you have an age value and for which you have a value income estimate. And it could very well be that, for instance, for all the cases in your data you have both age and income estimate, but for, let's say, these variables that you have over there you do have a couple missings. That would be that in this case you get the correlation estimated only on the ones where you also have data of all these as well, and that this one will be estimated simply on all the cases where you have data of these two. And you see that in this example, data from last year. We actually have different numbers of observations. So here, if you look at these correlations over there and over there, you will see that there are slight differences here and there. And this is simply due to the fact that they are calculated on different sets of cases from your data. Okay. Well, so far so good. However, there were no probabilities, no distributions, no significance levels, and so on, just yet. So this must mean that we're sort of halfway, because thus far we did something with data. You looked at crosstabs and we calculated something, and in the end wanted to decide, is there a significant difference of some kind? And we need to do that here too. So let's see how that goes. The way to do it would be run that pairwise correlation command with an extra option behind it, SIG for significant, or significance, I should say. And what you then get back is not only the estimated correlations, but also the extent to which they differ from zero. So in this case, H0 is the correlation between X and Y is zero. And then we try to figure out how likely would the data be given that H0 is true. And here you see, for instance, in that one, the correlation between estimated income and current grade is 0.34. And here we reject H0, where H0 is that 0.34 is actually a zero in the population. Well, how likely would it be that the correlation is zero in the population and we get the data like this? Well, not very likely. So in this case, H0 is rejected. And I have added these orange lines for all the cases where the number that we get here is below 0.05. Try to increase it a little bit in size. Let's see. So let's look at the first part only. So we get these numbers over here. They're exactly the same as what we had before. These are the correlations over there. And what's beneath it is the p-value that you end up with. And this is slightly different from what we're used to in the sense that normally for every kind of hypothesis test there was something else in the output as well. H0, that's something that we need to know ourselves. Then there is a test statistic that's being calculated and of which we know the distribution. And given that this test statistic is calculated, we can try to figure out, okay, is this a weird number? If we flip a coin 1,000 times, this is 982. That would be weird. Well, here, this data doesn't tell us anything about the test statistic that is being calculated. And in fact, this is the test statistic that is being calculated. This thing over here, so this is the correlation, this is the number of cases in the sample, and this is the correlation once again. We're not going into the details of why that is actually working, but this is actually the test statistic that is being used. It has a known distribution, and that will give us in the end here the significance values, and there, and there, and there. So we get every once in a while that H0 is rejected, and for several cases we also get that it is not. Okay, let's see. Again, this is correlation. Correlation is related to simple regression, so it should be the case that we can find this too somehow in the output of the regression command. We can. Estimated income by age and the significance level, and we see here the correlation is 0.04 or minus 0.04, which is not significant because this value over here is 0.53, which is way above 0.05, and that same number we see exactly in the regression over there. Here we are testing that minus 38 that we found over there at the slope of our regression line, so it's a downward slope. H0 would be, that slope is actually 0, and here we see that we cannot reject that. And this 0.527 is exactly the same as 0.527 over there. And the fact that we cannot reject that here is also consistent with the fact that we have an R squared here that's nothing. It doesn't help us much to know how old a person in the data is to predict what they say they expect about their future income. Okay, so once more, now hopefully with a bit more substance to it. Correlation is the extent to which a straight line fits the XY scatter plot. The thing is called rho if it's about a population, or R if we calculate it in an actual sample. It's the Pearson product moment correlation coefficient, if you want to be posh about it. And it is the extent to which knowing X would be of use in predicting Y, as long as we try this using a straight line. So no all kind of wavy curves are allowed here. We're just trying to figure out if a straight line would fit. Okay, so that's the basic stuff. That in itself, not too complicated, I think, but there are a couple of weird things that go with these different kinds of topics that are good to realize. And we need to go through these one at a time, because not all of these are so intuitively obvious. Okay, so let's see. First, well, interpretation. I talked about standardized variables before, and here you see once again that regression of here of weight on height. I think in the other one I did it exactly the other way around. And this is without standardization. Then the interpretation was easy. Okay, for every extra centimeter here, we get an extra 0.78 of weight there. So we get 0.78 would be 0.78 kilos. That's relatively straightforward. If I first standardize these variables, then it's slightly different. Then we see, well, if height becomes 1 larger than it is, then weight becomes 1 larger, becomes 0.75 larger than it is. But yeah, 0.1 larger and 0.75 larger in terms of what? Well, for standardized variables, this is all measured in terms of standard deviation. So what you should say here is, if height gets bigger, 1 extra standard deviation, so you move 1 standard deviation to the right, then weight moves 0.75 standard deviations to the right. That's the way to interpret the data. Okay, that's, well, one that is sort of close to what we had before. Now something that is a little bit more further away, and causes a lot of misinterpretation. Okay, the main thing to go by here is that if you predict well, so if you have an R squared that's really high, that need not mean that you understand very well. And this is the example to show it. What I did was, let's see, I looked at, I think, the AEX, so at the stock exchange, and I took data from, I don't know, 20 days or so. I looked at what the AEX was, and what I try to do now is I create another variable, and that other variable is what the AEX was yesterday. And what I'm trying to do is I'm trying to predict tomorrow's AEX value by today's. And if I do that, here I actually did it for these 20 cases. It's pretty hard to see, but let's see how well we're doing here. Well, an R squared of 0.28, which is not too bad. So here I actually have the square root of that, or 0.53. Quite a decent model, correlation of 0.53 between these two variables, but I have understood nothing. Okay, the only thing that I say is, well, what it was yesterday is likely to be that tomorrow as well. So I understand nothing of the whole process. But my model is not too bad, actually. Same thing here for the weather. Here I predict, I think, maximum temperature by simply the maximum temperature of yesterday. So I do not understand the weather. I'm not a meteorologist or what have you, but if I simply predict, given that I know that today the maximum temperature was 6.5, for tomorrow I also predict 6.5, then I do quite well. I get a correlation, in fact, here of 0.7, which is not too shabby. This is also, of course, why a weather forecast needs to be really, really good to show that you actually have something to add, because if you just say, yeah, the weather tomorrow is going to be, well, sort of like today, this is quite good already. And you need to show that you're actually better than that. It's not so easy. Okay, so for all these cases we have prediction, fine, or at least not too bad, but understanding, no, nothing. We have no clue about how all this goes. Nevertheless, and that is the way the counterintuitive thing, for correlational research in psychology in general, let's say, the same Cohen that was that visited us last week for Cohen's D has given us a couple of guidelines as to what large and what smaller sizes are. So a typical correlation of 0.1 would be small but still interesting. 0.3 medium sized, and 0.5 is a large correlation for any kind of psychological research. And if you then actually look in the literature, in all the psychological literature together, which kinds of correlations we find, then it's typically like this. About a third, then we have values less than 0.2. About a third, we have something between 0.2 and 0.3. And in about a third, we have larger than 0.3. In a way, we argue the fact that we do not see many studies here where you have correlational values of, let's say, 0.9 is also because very often then the finding is not interesting. If you have something where you could say, well, the correlation between this psychological measurement and that psychological measurement is 0.9, then it usually is so blatantly obvious that that will happen that it's not interesting to write it down. So quite typically you are in the range that is way smaller than this. But that still leaves, of course, the question, for which we don't have an answer, unfortunately. How high should our R or R squared then be? Well, there is no rule. And I can't say that enough, actually, because I know that on the exam, people will say, okay, I find an R squared of 0.1. This is certainly a very poor model. Not right. This is a poor model if what you want to achieve is prediction. For prediction, then it's not very good, obviously. But to try to understand, that is a totally different thing. For instance, a really small correlation of 0.03, and this is roughly, if I'm not mistaken, the actual correlation between swallowing aspirin, I think once a day, on the probability of a heart attack. This is actually what you get if you have suffered a heart attack once. You get to swallow aspirin the rest of your life because it decreases the probability of a heart attack. The effect is really small, but it's small enough to be of interest. So, it could very well be, especially for these medical applications, that very small correlation values are actually good enough to go by. Or, the other way around, a huge correlation need not be important at all. If you find a huge correlation, for instance, a weather example, you have learned nothing, you've just predicted something from something else without understanding why that would be. In fact, usually if you have correlational data in psychology and you have an R squared of 1, the highest likelihood is that you've made a coding error at some point. For instance, if you somehow have created two variables that are pretty much the same by accident, and now you run a correlation between the two, you find correlation 0.95, start to work. In all likelihood, something's wrong. Okay, so let's see. Then, what would happen here if we somehow change the units in which the variables are measured? For instance, we have weight in kilos, and we could actually also look at kilos in terms of, at weight in terms of how many half kilos do you have? Okay, weight times 2. So instead of the 80 kilo that I weigh 160 half kilos, and that shouldn't make any difference, of course, to how well the line is fitting, and that's actually what we see here. We do see differences here. This coefficient now changes, and it is, not surprisingly, now exactly half what we had there. So these coefficients, indeed, they do change, but how well the model fits, none of that changes. So any change in the unit that you use to define your variable, that shouldn't matter at all for how well your model fits. And if you think you found that, then something went wrong. Let's see. Oh yeah. The scatter plot changes as well. This is also why it's really difficult to try to figure out what the right correlational value is just from the scatter plot. Because for this one and for that one, you get the same correlation actually. And the only reason that the plot looks different now is because we have scaled the value differently. So this is also why having, let's say, a rough idea about what the correlation would be from a scatter plot is useful, but don't take this to extremes because, well, things like this and that actually deliver the same number here. Okay, a couple more steps to confuse you even more. The correlation between two variables, it doesn't matter if you type one first and then the other. So the correlation between x and y is exactly the same as the correlation between y and x. Try it in Stata, it's no coincidence. If you look at the formulas, it's also no coincidence. You'll see that the role of x and y can simply be interchanged. It doesn't make a difference. However, What is sort of weird is that if you regress y on x or x on y, and you would think that you would get the same line then. It's not the case. Here you see, first, the regression of height on weight, and we get a coefficient 0.725 and 125, and an r squared over there of that 0.57 that we've seen before. Here I type the same thing, but with the variables interchanged. Now let's see what happens. Well, the fit doesn't change. And the fit, we see that from this part over here. So we have the 0.57 over there and over there. Everything is exactly the same. And here you have a different coefficient and a different constant. And you might think that you can easily deduce one from the other. Well, I think I have that prepared here. There. So this is the regression line that I find in the top table. Height equal to 126 plus 0.73 times weight. If I rewrite this simply with weight to the left, then I get weight equal to minus 173.42 plus 1.4 times height. This is just rewriting what I found here. Apparently that's the best fitting line. You might think, if I now type the regression the other way around, now I'm going to find that one. But that's not the case. Find this one. Sort of related, but different. And why is that? Well, that is because of this here. We're trying to define the best fitting line here. Measuring differences in the vertical direction. So we're measuring the difference in terms of y, vertical distance to the line. Would have been different if you would have measured distance not in the vertical sense, but towards the line, like this. But we don't. And that causes that if you interchange x and y, that is simply saying, okay, we're not defining now the best fitting line according to these vertical distances, but we're defining the best fitting line according to the horizontal distances. And that causes that the line itself is a different one, but nevertheless the fit is equally good. And it's hard to get your intuition, let's say, totally up to speed with that. But for sure you can see, if you simply look at this one, it's not happening. You might think that this is enough to get the other one. It isn't. Any questions up to here? All right.
Why don't we calculate the best line with the lines orthogonal to the regression line?
Yeah, this is because, as we have showed it now, it seems like, let's say, x and y are just two variables, and we're looking at two variables in the data, could be in any kind of direction. In principle, what we're aiming for in the slightly longer run is that we do not have a single predictor variable x to predict y, but a larger battery of predictor variables x to predict y. And then basically what we're aiming for is to get close to y. So in that sense, the vertical distance, or the minimization of all the vertical distances, that's what we're aiming for. But in principle here, you're right, we could have measured it in a different way. Or also, as I mentioned before, instead of squaring the differences, why not take the absolute value? That would have worked too. Okay, and finally, something not to confuse would be correlation and causation. For all the things, you try to imagine that the thing that you use to predict something else is somehow causally related, but it need not be. One thing that we know is, well, people with a higher income live longer. That is an empirical fact. So there certainly is a correlation between the two. But in all likelihood, the fact that you live longer is not only because you have higher income, perhaps in part, but not completely. So higher income in itself does not cause the fact that you live longer. But the money itself doesn't help. It's something else. Perhaps what you do with the money, or let's say the care that you can get with more money, but money itself doesn't work. Okay, then a couple of variables that we've disregarded for a while, and that are the variables that have order in them, but are not interval. So all kinds of questions where you have answers like this. Let's see, for the better than average variable, the answer conditions are, far below, slightly below average, average, slightly above average, or way above average. there's order in there, that's obvious, from left to right, they are from smallest to biggest, but we cannot, in all likelihood, say here that the differences between, let's say, what's it called, far below and slightly below are the same as slightly below and average itself. So we know that there's order in there, but the scale is not very well defined, and for that we have something to run a correlation on as well. It's called Spearman correlation. The other one was labeled after Pearson, this one after Spearman, and what it does is, instead of looking at the data that you have, comparing two columns, two variables in your data, with a correlation coefficient, you first rank order all the cases in your data, and you give rank numbers to all the cases in your data, and then calculate the correlation between these rank orders. If you do that, it's called Spearman's row, and it gives you the value similarly to what you would see before. All the same things, it's a Pearson correlation, but calculated on something else. So again, you can get negative values here all the way up to -1 and positive values all the way up to +1. And the Spearman command immediately gives you a test as well. H0 even gives you the H0 with it. The H0 here is that the two variables are independent of each other, or the correlation is 0, so to speak. And in this case, this one is not rejected. Because you have to rank order your cases here. If you have many cases in your data with the same value, that's a bit of an issue, because how should I order, let's say, 25 cases in my data if I'm, let's say, ordering age? First, we have people who are all 18. A rank number given to that, we have to somehow take into account that there are ties in the data, so that makes that the formula is a bit complicated. But still, it can be done, and the only thing that you need here is that there is order in the data, and not even that they are interval scale. Okay, one more weird thing that we need to look at here, that is trying to bring home the message that whatever you do, look at the scatter plot before you do the actual calculations. This is a quite famous data set, a data set with only 11 cases and with 8 variables in it. It's called the Anscombe data, and we have an x1, a y1, an x2, a y2, all the way up to an x4 and a y4 in the data. Now, if you look at what they appear to be, then we have this, a mean of 9 for all the x's, for x1, 2, 3, and 4. And for all the y's, we have a mean of 7.5. And even the standard deviations of the x's and the y's are exactly identical. So, if you look at these, then for all practical purposes here, there is no difference between all the x's and there is no difference between all the y's. Also, if you look at the correlation, still you get the same number, 0.8164 in all cases. The correlation between x1 and y1 is that number equal to between x2 and y2 and so on. So these all appear to be the same. And this is typically what you get as soon as you forget to look at these scatter plots for all practical purposes. Because the data, in fact, look like this. So this is x1 and y1 in the top left. Sort of a cloud of dots, as we are getting used to now. x2, y2 looks totally different. Okay, you can fit a straight line through here, but I certainly see a better option than a straight line in this graph. There, a straight line with one outlier over here. So this is, again, totally different. And here, all cases with similar values over here and one dot over there. None of that you would see from all the stuff that you have over there. They're all the same. If you look at the plot, it is relatively easy to see. Not a problem whatsoever. And something else you see from here is that correlation itself is quite sensitive to a couple of weird cases in your data. Here you see what the the best fitting line is in blue. Now you can imagine if that one wouldn't have been there, that the line would certainly have been somewhere else, slightly lower. And we have to later on figure out ways to try to find these kinds of cases when we have data that is a bit more abundant than 11 cases or so. It's not so easy anymore if you have 20,000 cases. Here too, if this case wouldn't have been there, now the best fit is this line. Forget that case, and the best fit will be that line, which is a quite serious difference from where we started. And that makes a big difference for correlational values. All the stuff that we want to calculate here are apparently quite sensitive to losing a couple cases from my data. another 1 over, well, in this case 2 over square root n rule that is of use here. If we have in our data a correlation coefficient that we calculate, and we are trying to wonder here, would that be significantly different from 0 at all? Then this is the rule of thumb that you can use. If that R value that you find, an absolute value, is larger than 2 over the square root of n, where n is the number of cases in my sample, then it's likely to be statistically significant. In a way, this is sort of weird, because this means that if my n is large enough, and I have a really, really large sample, then in the end, this thing, of course, will be really, really close to 0 and will be smaller than whatever R I have in my data. So let's suppose that I find an actual R here of 0.01, which is really close to nothing. If I have a sample here, there, that is big enough, then that number on the right here will certainly become smaller than that, and we will conclude, yes, that 0.01 correlation that we found is indeed statistically significantly different from 0. So this is showing, well, large samples, anything will become statistically significant. And this is in fact why we talked about effect sizes so much, because effect sizes show you if it's interesting what you find, and statistical significance you can get, yeah, given that you have a large enough sample, always. So let's see for I think I have a couple of examples. No, I missed those, okay. So just to get a feel for this, n equal to 100, square root of that, 2 over 10, so an R, a correlation of 0.2, that will be significant in a sample of 100, roughly. In a sample of 900, well then way smaller R's will even become significant. And if you remember what the plots look like for R's of, let's say, 0.1 and below that, that is pretty close to sort of random noise. So you could be mistaken from just looking at the scatter plot, this is close to nothing, but then still you might have correlations that are statistically significant. Okay, so the big thing to get from this is don't go totally out of your way only trying to show statistical significance. That's part of it, of course. We're trying to find very often cases where we find statistical significance, but that certainly is not necessarily the same as substantively interesting. For a huge sample in particular, anything will become significant, and you have to think about if it's interesting from a substantive point of view, where substantive very often simply means knowing what you are talking about. So if I want to try to figure out who owns an Android phone, so to speak, and I want to compare two groups, and 30% is the score for males, and 30.0003 is the score for females, and if I have a very large sample, that difference would even become significant. Yeah, nice, but substantively this is of no practical use, so let's forget all about it. That would be the main lesson for this one. Okay, this part I want to skip. Short recap of what we had this far. Correlation and partwise correlation. You need to know the difference. Both calculate correlation for you, and they differ in the way in which they deal with missing values. Second, it's all about looking at a scatter plot and trying to fit a straight line through a cloud of dots. A straight line, nothing else. Simple regression, so trying to predict y from a given x is actually what's happening behind the scenes and is closely related to these correlation values. Stata will find the line that fits best for you. And in several ways we've seen that correlation and simple regression are related. Standardize the values and look at the coefficient, then look at the R squared, and then take the square root of that, you get the correlation. That'll work too. Excuse me, the people over there, could you shut up for a minute? I've seen it happening now for 20 minutes. I'm fed up. Tried to sit it out for the next 8, but it's not working. Then prediction and understanding, totally different. I can create quite easily a very large R squared, need not mean that I understand anything. Yeah?
Why would you ever use correlation if you go
That will become important when we have a larger set of predictors to predict a single interval variable. Because then, if I want to predict some y variable, let's say tomorrow's AEX, or tomorrow's stock index, from let's say 10 variables, and what Stata will do automatically is calculate a prediction there for all the cases in my data for which I have actual data for all these variables. And then the correlations that I will look at are simply the ones for the correlations that will end up in my analysis in the end. Because all the other ones that have some missing here and there won't be in the analysis anyhow. So in that case, it starts to become important to look at that correlation command and not at the part. Yeah.
So in that case, if you use the pathwise correlation, will you get wrong results?
Well, usually what you're doing is you would look at these correlations to get a feel for which of these variables might be of use in predicting whatever it is you want to predict. And then what could happen is that you use pairwise, that you see that there is a quite strong correlation between the two, but the correlation is calculated not on the cases that will be used in your analysis in the end, but on the way larger sample. So in that sense, it's not a good idea to then use that pairwise. If you simply want to look, in general, in my data, what are the correlations between the variables, then I would suggest you look at the part. Anything else on this? Then a sort of a poor man's version, Spearman's row on the variables that are not really interval, but for which we only know that there is an order in them. We then first rank order the cases and then calculate a correlation. The typical test, the H0 that is being used here is the correlation is 0. In principle, you could test against any value there. So if you want to test, might the correlation be 0.15, you could do that too. But the standard output that say they will give you is all related to equal to 0. And effect sizes, let's say anything of 0.5 or larger is large, 0.3 or so is medium, 0.1 or so is small. And that's, let's say, what we're used to in psychology, at least, in terms of what is interesting and what is not so interesting. Any questions about this? Otherwise, I'll skip to the information about the test of next week. Okay, test on December 7th. The material is basically everything up to today. So that gives you another week to digest or get back on track if you are lost. The test itself will be on your own laptop, so you'll have to bring your laptop. You can use Windows or Mac or Linux or whatever you have. It's totally browser-based, so you're necessarily allowed to use the browser, but nothing else. So no Stata, no other stuff that you have there, no slides, no nothing. Just the browser and your brain. We will see how that goes. As soon as you are caught doing something else, then the only thing to do on my account is that I report you to the exam committee and they'll take it from there. It's a wise idea, I think, to try to make sure that you can switch off everything that will look suspicious. So all kinds of standard messages that you might get from who knows where, all of that should be turned off. Let's see. Yeah, then one thing that may be slightly different from what you're used to, when you're done, then you can leave. But when you leave, you have to check out, because I need to check that you actually delivered all the stuff. Because otherwise, what you could do is, you close your laptop, you move outside of the room, and you continue working over there. So I have to make sure that as soon as you leave, that indeed you have delivered the actual test. And you should check out either with me or with an attendant. There will be a couple of attendants there as well, I hope. Yeah. No, the test will be in the study hub. So that's in the pavilion building where other exams usually are, not here. So you will have current for your laptop and a separate desk for yourself. The test itself will be, I don't know exactly yet, either completely multiple choice or largely multiple choice. And if it's largely multiple choice, the ones that aren't multiple choice will be short answer questions where I ask you for a number or a single sentence or something of that kind. And on hours 7 and 8, in all likelihood, hour 7, I'm not completely sure if I'll be able to make it exactly on time, but at least I will continue then back here. First by going through the test itself, look at the questions that have been answered the worst, and go through that, and then I'll need to continue for 1 other hour with the rest of the material. Any questions about that? Yes?
Could you upload the test, or similar test to what we'll have to do?
Yeah, okay, so the question is, of course, what can you expect there in the test? I can give you a couple of example questions. It's not that far-fetched. There are, roughly speaking, 2 kinds of questions. The one kind is where I ask you, let's say, a knowledge question, as in, what is a chi-square distribution? Or when do you use a Fisher's exact test? And the other kind of question would be, I give you output from Stata, and I ask you something about it. What do you see here? Is there a relation between X and Y? Or something of that nature? And these are the kind of questions